recording has started. So, done. This is going to be a classic class recording, I'm pretty sure.
It's going down in the books.
Yeah, this is, in the history of class recordings, this is going to be way up there, I can tell already.
Hi, Sebastian.
Feel better.
And a personal shout out, too. It's like a long distance dedication. So.
Oh, there's a second page?
Just actually reading.
Wait, does Sebastian even have these pages?
No.
Which means it's luck on Monday.
All right. So here we go. Over the past couple of days, we've been working through this presentation that is called How Do We Get Charges to Do What We Want Them to Do? Those three headings, or subheadings, electrical potential energy, voltage, current, resistance. We started off with the fact that it's talking about charging, what do we want them to do, implies that they can do stuff. And we said that there's an energy topic, an energy factor that we talk about here. And that energy that we discussed was, come on, there we go, electric potential energy. There we go. Electric potential energy, which talks about position of an electron within an electric field, or within an electric field. And we talked about how moving that charge around in the electric field can increase energy or decrease energy. And then we talked about how the strength of the electric field can also change the energy because it just does more stuff to that particle. And that led us into voltage, where we talked about the ability of an electric field to change the energy. And yesterday, we followed this electron around through its path, looking at the increases in energy and the decreases in energy, and ultimately going from one side of the battery to the other side of the battery causes it to lose all of the electric potential energy that it gained going through the battery. The battery does work, increases the electric potential energy. As the electron travels through the circuit, it loses all of that electric potential energy, and it's turned into other forms of energy. Yesterday, we introduced the idea of current, where current is the movement of charges. Usually those charges are negative electrons, but they don't necessarily have to be. And we talked about how we define current and how we measure current. So, if we're looking for real simple analogies or real simple connectors between the terms, voltage tells us about what? The electric potential energy, or energy in general. Current tells us about what? Go ahead. Charges, specifically how many charges there are. Voltage is an energy thing. Current is how many charges are there. There is one more part to this story. And it starts here. Back in the first outline that we talked about in this section, we talked about conductors and insulators. And we talked about the idea that certain atoms hold on to electrons more strongly than other atoms. What kind of electrons are we talking about specifically? Valence electrons. Electrons on the outer edge. And remember we talked about the idea that conductors, those outside electrons, are loosely connected to an atom, but that they can flow from one atom to the next, and that allows the charge to flow. But insulators, on the other hand, hold on to their valence electrons more tightly, which doesn't allow those charges to flow. How tightly we hold on to those electrons leads to our discussion of resistance. Resistance, defined as the impedance to charge flow through a material. If you want to sound smart, just bust out impedance on somebody. Basically means resistance, like making it hard. If you're impeding something, that means you're making it harder. So, or in regular person words, how hard is it to make charges move through the material? That's what resistance tells us about. What?
No, I like this word.
Say again?
I think the word is
Actually, if you look at the next thing down on your outline, it is in normal people words.
I just sort of mean
Science is accessible to everybody. People with big vocabularies and small vocabularies. Doesn't matter. We can explain it either way. I'm not making a judgment. I'm just saying it is.
I mean, it's I like big vocabulary only like not in science. Yeah,
That's cool.
because science is hard enough to understand.
Some materials allow charges to flow more easily based on the previously stated factors. Instead of previously stated factors, might be a good idea for you to write down how tightly they hold electrons, or how tightly they hold valence electrons. Some materials allow charges to flow more easily than others based on how tightly they hold valence electrons. Conductors don't hold valence electrons real strongly. There's still an attraction because we're talking about a positive nucleus and a negative electron, so there's some attraction there, but the attraction isn't as strong as in non-conductors and generally non-metals, insulators, where those charges don't flow very easily at all. More good news. On your outline, letter D says factors that affect resistance, and then there's 1, 2, 3, and 4. Apparently I took that out of my presentation last year and didn't take it out of the outline. So you're not responsible for letter D or number 1, 2, 3, and 4. So you can cross it out or whatever you want to do, or just leave it blank, whatever. But you're not responsible for that section.
Are you going to tell us?
No, because I'm not going to test you on that. So I'll tell you. Temperature, length, cross-sectional area, and the material itself are the 4 factors that
What was the third one?
cross-sectional area,
Come on, you should know that.
like this, like the diameter of the conductor that we're talking about. Is it a big fat wire versus a real skinny wire? The nature of the material itself. Is it a conductor? Is it an insulator? Picking it up on letter E, resistance is a relationship between. That relationship is summarized by this equation up on the board. R is probably going to stand for what? Resistance. V, voltage. And then I, current. We introduced that yesterday. So, resistance is the relationship between voltage and current. Comparing how much energy do those electrons gain as they go through our battery or our voltage source versus how much or how many electrons move because of that energy gain. The SI unit for measuring resistance is the ohm. The Greek letter that is we use to represent the ohm resistance is omega. What? Is that overpriced? Seems overpriced, but I really don't know. So, well, I know what leggings are, but I don't know if $80 for them is overpriced.
You could get them for like 10. I think you could get them. Yeah, you can buy them.
Like,
I'm gonna get myself.
Yeah, they're
that's cool. Whatever works for you.
The ohm, the ohm is the ohm represented by omega. That's a capital omega, by the way. There's lowercase omega too. It looks like a curvy W, but it's short for a different thing. So. A curvy W. The ohm is defined as 1 volt for every 1 amp. Remember, amp is the abbreviated version of the ampere, which is our unit for current. So the voltage, or the resistance unit, incorporates both the voltage and the current. There is a reason why it is called that. Although an amp is an amplifier, so it makes things bigger, which is different than an ampere, which measures current. But there is some, it does have something to do with that, though. The 3 factors that we have introduced in this presentation: voltage, which deals with energy; current, which deals with the number of electrons that are traveling; and then resistance, the impedance to flow of those electrons, describe how we can get those charges to move through a path to get them to gain energy and then ultimately turn it into other forms for what we want it to do. Those 3 factors come together in something that we refer to as Ohm's law. Notice that the same 3 factors that were in the definition of resistance show up in Ohm's law. We've just rearranged them. So Ohm's law, V equals IR. Voltage equals current times resistance. And we can talk about how those 3 things interact with each other at different parts of the path that these electrons travel, going from high potential energy to low potential energy. Good there? Okay. The last part of your outline, superconductivity. Read the sentence there. It basically tells you what. Over the next couple of days, we will look at how these 3 factors interact with each other so we can get these charges to do what we want them to do. And we get them to do what we want them to do through something called an electric circuit. A set of components connected to provide one or more complete paths for the movement of charge. Going back to yesterday, if we need a path for the movement of charge, why do we need a path for the movement of charge? Why do these charges move? Doing good. Absolutely. So, the spot that they don't like, why don't they like that? What do they have in that spot? The same charge, but what does that do? Yes, they repel each other. That causes them to have how much electrical potential energy? High or low? High. So, the battery does work on the charges and causes them to go or get a high amount of electrical potential energy. They don't like having a high amount of electrical potential energy, so they move in a way to get to low electrical potential energy, right? Which is basically moving away from things they don't like towards things that they do like. That's what the circuit provides for these charges. But it also has to have a way for them to gain the energy that they need to lose. So this, while not in your outline specifically, is the important idea that we have to keep in mind over the next couple days as we're analyzing these circuits. It's a matter of increasing potential energy and then allowing to that potential energy to decrease by turning it into other forms. Right? Remember, it doesn't just go away. Energy is conserved, but we increase potential energy and then we decrease it by turning it into other forms. And that's what the circuit does. Good? Keep that in mind over the next couple days as we talk about this. So, closed circuit. A closed circuit is a complete path of conductors for current to flow from a location of high electrical potential energy to low potential energy. Right? Or from one side of the voltage source to the other side of the voltage source. A complete path of conductors we refer to as a closed circuit. And like we just discussed, those charges are going from high potential energy to low potential energy. Or from the side of the battery they don't like to the other side of the battery that they do like.
So they technically flow through the light bulb.
Yes, that light bulb has a certain amount of resistance, and in that way, the resistance of the light bulb transforms electrical potential energy into heat and light. And that's what resistors do. They turn potential energy into other things. Could be heat and light for the light bulb, could be sound if it's a speaker, right? Some other form of energy, but that's what the resistors do. An open circuit means that there is no complete path for the charge to follow. It doesn't have a way for it to get from the area of high potential energy to low potential energy. And as a result, the charges stop. There is no current in an open circuit. So if there's a break anywhere in the circuit, and they don't have a complete path to get back to the other side of the battery, the current will stop. The third kind of circuit that we want to watch out for is the short circuit. A short circuit on your outline is a short circuit with very low resistance between the terminals of the battery or the voltage source. The current is very high. Going back to Ohm's law, V equals IR. Low resistance allows high current. So with very low resistance between the terminals of the voltage source, the current is very high. And that's your next phase. But along with that very high current comes heat. Those electrons have to lose the energy somehow. If there's no resistors there to turn it into light or sound or movement, one of the forms of energy that electrical potential energy gets turned into is heat. If enough heat is released, that starts damaging the conductors themselves, right? A metal wire will melt if it gets too hot. And that happens a lot of times with a short circuit. Or the metal wire that's traveling through your house next to the walls or through the walls of your house, like through wood and drywall and things like that, if it gets too hot, they can cause those things to catch on fire. And that's what we generally refer to as an electrical fire. So the short circuit, the resistance is very low, which causes the current to be very high, and that generates a lot of heat. Okay? Good? We usually classify circuits in one of two ways. We usually classify closed circuits in one of two ways. The first is a series circuit. The series circuit provides a single path of conductors for the charges to follow. And that means that the current in every part of a series circuit will be exactly the same. And if there's only one path to follow, we can add resistance by adding more things into that path. If we add a fourth light bulb into this circuit, all of the conductors, or all of the charges have to travel through that fourth light bulb. So that adds more resistance, and with more resistance, generally what happens? You either need more power, or if you have the same power, you get lower current. Are we ready for an analogy?
Yeah.
Okay. So, let's talk about these two types of circuits, in terms of something that's relevant because it just happened recently, Black Friday. All right, now Cyber Monday doesn't work for this analogy. So Black Friday. People go to the store with a lot of potential energy in the form of what? Money. Over the course of their trip through the store, they want to turn their money into products, right? Large TVs for a great price, right? However, you must pass through one point in the store in order for that to happen. The cash register. The cash register is the resistor in that circuit, right? That turns your cash into TVs, right? What would a series circuit on Black Friday look like? Not a bunch of cash registers, one cash register. Because everybody has to go through that cash register. One path for current to flow. And we could slow the current down, right, by changing the resistance at the cash register, right? If you have a really chatty sales lady, right, she's slowing everything down. Sorry, shouldn't stereotype. I'm going to stereotype a little bit here today, okay? But right, if they're generally right, if you have like an old lady, right, she wants to know how Thanksgiving went, right? You know, if you guys went shopping, she wants to know if you got to see the grandparents, right? You know, she's chatting you up when really all you want to do is pay your money and get your money and turn it into a TV, right? And then, right, we've added a security guard at the door who's checking your bag. Maybe you don't carry your TV out in the bag, but he's checking your receipt, right? But that adds another resistor. That slows everything down. And if everybody has to go through that, right, that impedes charge flow. Good?
Yeah.
Okay. In order to fix that, what could we do?
Steal stuff.
Add more cash registers. That's a closed circuit. That's an open circuit. That's the little buzzer thing by the door that prevents flow of products. So parallel circuit. A parallel circuit provides multiple paths for current to flow. We've opened more cash registers. Let's talk. Okay, so let's do our analogy, then we'll put it real terms to it. Okay? Just because there are multiple cash registers open, does that mean people first, at every cash register, what has to happen? Scan stuff and turn money into TVs, right? Okay, or products, right? That happens at every cash register. So every path in the series circuit has to provide a way for charges to go from high potential energy to low potential energy. Because that's what a circuit does. So every cash register has to turn money into products. Every path of the series or the parallel conductor has to turn high potential energy into low potential energy. But just because there are multiple paths, does that mean that the flow of product through each cash register is exactly the same? Little old ladies want to talk to you while you're checking out, right? But if you, sorry, I'm going to stereotype a little bit here, right? Little old men, right? Little old men, right? If you have a chance, like if you have a choice to go to cash registers, and there's an old lady and an old man, go to the old man register. Why? Old man doesn't care about Thanksgiving. He doesn't care what you did yesterday. All he's doing is sliding the product across the beeper, right? Okay. No, see, it's like if they're older guys, like really old, right? But like kind of like kind of like a like a. So. Right, you know that certain registers at Target, right? But there's certain guys, right? It's usually guys, right? That are just like, they don't want to talk to you. They don't even say, like when you walk up to the register, they're not even like, hey, how's it going, right? They're just like, they start grabbing stuff and just, right? Because they just want you out of their face, right? Right. But, right? We'll stereotype a little bit here, okay? But the teenagers that are working, right? Nobody, they're just not, they just don't want to be there, right? So it's like, the hip is definitely. So, if only, good thing this is only an audio class recording. Oh, that's Sebastian. Yeah, Sebastian's like, what's going on? So, but. But. So. The characteristic of the cash register, or the personality of the cash register, or the person working the cash register, would be like what? What term would that go along with? That's the resistance, right? How easy is it to get product to flow through your cash register? As a result, even though at every cash register we're turning money into products, does that mean there's the same number of people going through each cash register? Not necessarily. Okay? So, now let's put things into your outline. Okay, Julie, go ahead. Cool. Yes, that's fine. There could be, right? That would be like a different, that would be like, so on, let's say, an MP3 player, right? An MP3 player like with a built-in speaker, let's say, okay? There has to be some charge that lights up the screen that tells you what song is on, but then there also has to be another part that plays the music. Does that make sense? Yeah. So there, you're talking about a parallel circuit where some of the charges go to the screen, lighting up, telling you what song is on, and other charges go to the speaker to turn their electric potential energy into music or into sound. Does that make sense? Yeah. So yeah, I mean, it depends on what path we're going and stuff like that. And just because they're all going from one side of the battery to the other side of the battery, doesn't mean that we have to have the same number of charges go to the screen as go to the speaker. The screen might take more charge because it might need more energy to flash the name of the song or whatever than the speaker does to make the sound. So you send more charges that way and less charges this way. The way you do that is by changing the resistance. If Walmart wants to get more people to go through their cash registers, they change the resistance of the people working the cash register. Hey, slow lady, get out of here. Let's let this guy do it because he goes faster. We're good.
I actually went to Walmart and there was a lady there who was like,
Right. Right, she's trying to keep it like, or she's trying to make sure that the current keeps flowing, right? And if there's one cash register that doesn't have anybody at it, that cash register has, at that point, a low resistance. So more current goes that way, Same idea. Maybe that's it
We
too.
want to be that old lady and be like, Grandma, what do you do for a job? I tell people where to go to check out.
Hey, you know what? Pays the bills.
All right, so,
Don't hate.
Appreciate.
all right, listen up. So let's fill in this outline here, okay? So, letter B, each part of the circuit is connected to the voltage source, meaning that each part of the circuit has to turn high potential energy into low potential energy. And that means for letter C, the voltage across each component is the same. At each register, we turn money into TVs, regardless of which register you go to. That's what happens. That's letter C. The voltage across each component is the same. This relates to, put this in your own words, this relates to the idea that charges have to go from high potential energy to low potential energy, regardless of which path they take. That idea that the voltage across each section is the same is based on the idea that charges have to go from high potential energy to low potential energy, regardless of which path they take. I know. I say like you might want to like summarize that somehow, but I know you were like zoned out. I was actually reading off of her outline. The last part, letter D. The total current is the sum of the currents of all the paths put together. The current through each path can be different, but letter D says the total current through the circuit is the sum of the current through each conducting path. So tomorrow, we are down in the computer lab.
Yeah.
You can go straight there. I will put a sign on the door to remind you in case you forget. Okay?
Wait, which one?
I forget.